I said, "Burr, it's cold in here." I said there must be some areas of regular polygons in the atmosphere.
First thing we're talking about is a regular polygon. That would be a polygon that's both equilateral and equiangular. So we've talked about this before, but it's worth mentioning again because that's what we are finding the area of today, regular polygons. So again, a regular polygon has all sides congruent and all interior angles congruent. Next, we're going to talk about the center of a regular polygon. That would be the center of the circumscribed circle. So in our examples down here, we have an equilateral triangle, ABC, and we have a regular pentagon, DEFGH. Now, in each of these regular polygons, the center of that regular polygon is the center of the circumscribed circle about each of those regular polygons. Now, a radius would be the distance from the center to a vertex. So, we just talked about how to find the center of your regular polygon. The radius is just going to be the distance from the center of your regular polygon to a vertex, one of the angles. Now, we normally deal with radii in circles, but this makes sense if you think about it, because if you were to circumscribe a circle about each of these regular polygons, a radius is going to be the distance from the center of your circle to a point on the circle. And look, your vertices are points on the circle. Therefore, a radius of your polygon is the distance from the center of the polygon to a vertex. Next thing we're talking about is a central angle of a regular polygon. That would be an angle formed by the center of the polygon and the endpoints of one side of the polygon. So when we typically hear central angle, we think about an angle within a circle that has a vertex at the center of the circle. But here, we're talking about the central angle of a regular polygon. And a central angle of a regular polygon is still going to be an angle with a vertex at the center of your polygon. It's just this time, the sides of your angle have to connect to the endpoints of one side of the polygon. And that makes sense because if you were to circumscribe a circle about that polygon, this central angle of your regular polygon would also be a central angle of that circumscribed circle. Next vocabulary term is an apothem. That would be the perpendicular distance from the center to a side. So down here you can see a couple examples of apothems. Segment GM is an apothem of equilateral triangle ABC because it's the perpendicular distance from the center of that polygon, point G, to a side of the polygon, segment AC. Over here, segment KJ is going to be an apothem of regular pentagon, DEFGH, because it's the perpendicular distance from the center of that pentagon, point K, to a side of the pentagon, segment ED. Now let's talk about the area of a regular polygon. So the area of a regular polygon is half of the product of the apothem and the perimeter, or area is equal to 1/2 A times P. So if you are given that a polygon is regular, meaning it is both equilateral and equiangular, and you want to find the area of that regular polygon, you're going to use the formula area is equal to 1/2 the apothem times the perimeter. So if we're looking at this example, for this equilateral triangle ABC, if I want to find the area of this, what I would do is I would multiply 1/2 times the apothem, the measure of segment GM, times the perimeter, the measure of each of the three sides added together. If I want to find the area of this regular pentagon, what I would do is I would take 1/2 and multiply it by the apothem, the measure of segment KJ, and then multiply that by the perimeter, the measure of all five sides added together.
Rah, example time. If you can't do it, I'll do it.
Now example 1 says, given the following equilateral triangle, find the measures of the given angles. So first, we're going to find the measure of angle ADB. Now angle ADB would be a central angle of this equilateral triangle, ABC over here, because it's an angle formed by the center of your polygon and the endpoints of one side. Now in order to find the measure of a central angle of a polygon, what you're going to do is you're going to take 360 degrees and divide it by the number of sides. So in this case, we have a triangle, meaning it's a three-sided polygon, so we're going to take 360, divide it by 3. That will give us the measure of this central angle, which is 120 degrees. Next, we're going to find the measure of angle CDB. So angle CDB would also be a central angle of this equilateral triangle ABC because it's an angle formed by the center of your polygon and the endpoints of one side. So in order to find the measure of a central angle, you just take 360, divide it by the number of sides, three sides in this case because it's a triangle, and you get that the measure of angle CDB, this central angle, is 120 degrees as well. Next, we're going to find the measure of angle BDE. So angle BDE, this is not a central angle this time. Instead, it's this angle right here where we have that central angle, angle CDB, that we know is 120 degrees, but we have dropped an apothem here, segment DE. Anytime you drop an apothem like this in a regular polygon, what's going to happen is it's going to take the measure of that central angle and it's going to divide it in half, meaning that if this whole central angle was 120 degrees, your apothem is going to cut it into two 60-degree angles, meaning the measure of angle BDE would be 60 degrees.
Dribble it, pass it, you should try it.
Okay, first we want to find the measure of angle HKG. So angle HKG we see is a central angle because it's an angle formed by the center of your polygon and the endpoints of one side of the polygon. So in order to find the measure of a central angle, what you're going to do is you're going to take 360 degrees and divide it by the number of sides in that polygon. So we see that this is a regular pentagon, meaning it has 5 sides. So we take 360 divided by 5. We get that the measure of a central angle, or angle HKG in this case, would be 72 degrees. Next, we want to find the measure of angle IKH. So angle IKH would be the measure of this central angle right here because it's an angle formed by the center of your polygon and the endpoints of one side. Therefore, in order to find the measure of that central angle, we take 360, divide it by the number of sides because it's a regular polygon, that would be 5, and you end up getting the measure of angle IKH. That central angle is also 72 degrees. Next, we want to find the measure of angle LHK. Well, this is a little different because this is not connected to any of the central angles. This is this angle over here. Well, how do we find that? Well, as you can see, segment KL is our apothem here. And when we drop our apothem, it is perpendicular to one of the sides, meaning that this angle right here has to be 90 degrees. So we have a little right triangle here. We also know that when we drop our apothem, that's going to cut our central angle in half when we're dealing with a regular polygon. So if the measure of our central angle, angle IKH, is 72 degrees, and our apothem is going to cut that in half, that means that the measure of angle LKH is going to be half of 72 degrees, or 36 degrees. And now all I have to do to find the measure of angle LHK would be to take 180 degrees, subtract 90 degrees, subtract 36 degrees, and I'm left with 54 degrees. That's the measure of angle LHK. Now example 2 says find the apothem and radius of the equilateral triangle using special right triangles. So today, what you're going to have to do is find the area of a regular polygon using the area formula. Area is equal to 1/2 the apothem times perimeter. And you're going to have to find the apothem of your regular polygon just given one of these side lengths. So let me show you how this works. In order to find our apothem and our radius, the first thing you're going to do is you're going to create a central angle and find the measure of that. A central angle is an angle formed by the center of your polygon and the endpoints of one side. So we're going to have to locate the center of our equilateral triangle here. We'll call that point D. Then we're going to draw a central angle connecting the center of your polygon and the endpoints of one of these sides. Next, to find the measure of this central angle, you just take 360 degrees and divide by the number of sides. Here we have a triangle, so that would be 3 sides. We end up getting that the measure of the central angle is 120 degrees. The next step is for you to drop an apothem going from the center of your regular polygon so that's perpendicular to one of the sides. So I'm going to draw an apothem going from point D so that's perpendicular to this side over here, segment CB. Now that I've created my apothem, there's 2 things I want you to note. The first would be that because this is an equilateral triangle, that means that all these sides must be congruent. So if this side length over here is 12 rad 3 centimeters, that means this side over here is also 12 rad 3 centimeters, meaning this side down here is also 12 rad 3 centimeters. And when you drop your apothem, it's actually going to bisect this side length over here, meaning the measure of segment CE and the measure of segment EB are both going to be half of that given side length. So they're both going to be 6 rad 3 centimeters. The second thing I want you to note is that not only does this apothem bisect this given side over here, but it also bisects your given angle. So step 3 is to divide this central angle in half, meaning if this whole central angle is 120 degrees, each of these smaller angles are going to be 60 degrees. Now, how does that help us? Well, we have now created 2 little right triangles down here where one of the acute angles is 60 degrees. That means the other acute angle must be 30 degrees, meaning we have created a little 30, 60, 90 degree triangle. And in a 30, 60, 90 degree triangle, everything is based on the short leg. The short leg is the side opposite your 30 degree angle. If I multiply that by 2, I get the hypotenuse. If I multiply that by rad 3, I get the longer leg, the side opposite the 60 degree angle. So if I'm looking for my apothem or my short leg in this 30, 60, 90 degree triangle, what I'm going to do is I'm going to take the longer leg that I'm given and divide that by rad 3. That should give me the length of my shorter leg or the length of my apothem, which in this case would be 6 centimeters. And like we said, we're finding the apothem and we're finding the radius. So in order to find the radius or the hypotenuse of this 30, 60, 90 degree triangle, I'm going to take the length of the short leg, which is 6 centimeters, multiply that by 2, and that should give me the length of segment DB, or my hypotenuse in this 30, 60, 90 degree triangle, which is 12 centimeters. Now I know my apothem of this equilateral triangle is 6 centimeters. My radius is 12 centimeters.
It's a you try time. A you try time. Here we go.
Okay, doing the same thing. I'm again given a regular polygon. This time it's a regular hexagon, and I want to find the apothem and the radius. So the first thing you're going to do, if you want to find the apothem and the radius, if you're only given one side length of a regular polygon, is find the measure of a central angle. So a central angle is an angle formed by the center of your polygon and the endpoints of one side. Well, because they don't give you the center of this polygon, you're going to put it there yourself, and you're going to draw a central angle. Next, what we're going to do is we're going to find the measure of that central angle. And we know in order to find the measure of a central angle, you just take 360 degrees and divide by the number of sides in your regular polygon. In this case, that would be 6 sides, so 360 divided by 6 gives you 60. That's why the measure of our central angle here is 60 degrees. Now, step 2, we are going to drop an apothem going from the center of our polygon so that it's perpendicular to this side down here. When I do that, there's 2 things I want you to note. The first is that since this is a regular hexagon, all of the sides are going to be congruent to each other, meaning that if this side length is 8 kilometers, all of these side lengths are 8 kilometers, including this one down here. And when we drop our apothem, it's actually going to bisect this side, meaning each of these little segments right here are going to be 4 kilometers apiece. The second thing I want you to note is that not only does this apothem bisect this given side over here, but it also bisects your given angle. So step 3 is to divide this central angle in half, meaning that if this whole central angle is 60 degrees, each of these little acute angles in here are going to be 30 degrees. Now what happens is we now have created these 2 little right triangles here, and in this right triangle over here, we have one of the acute angle measures being 30 degrees, meaning that the other acute angle measure is going to be 60 degrees, meaning we have created a 30, 60, 90 degree triangle here. Now, with our knowledge of 30, 60, 90 degree triangles, we can find the apothem and the radius of this given polygon. So how do we do that? Well, in a 30, 60, 90 degree triangle, everything is based on the short leg, the side opposite the 30 degree angle. The short leg times 2 gives you your hypotenuse, whereas the short leg times rad 3 gives you your longer leg, the side opposite your 60 degree angle. So if I wanted to find the apothem here, which is the longer leg, the side opposite the 60 degree angle, I just take the length of the shorter leg, 4 kilometers, multiply that by rad 3, and I get that our apothem here is going to be 4 rad 3 kilometers. If I want to find the radius, which would be the hypotenuse here in this 30, 60, 90 degree triangle, I just take the length of the shorter leg, multiply it by 2, I get the radius is 8 kilometers. So I have successfully found the apothem and radius of this regular hexagon. Now, example 3 says find the area of the regular hexagon below. So we know that this hexagon down here is regular, meaning all of the sides and all of the interior angle measures are congruent. In order to find the area of a regular polygon, we know the formula is area is equal to 1/2 the apothem times the perimeter. In this regular hexagon, we are given the length of our apothem, which is 10 inches, so we can plug that in for our lowercase a right here. But what about our perimeter? Well, since it's a regular hexagon, we know that all of these sides must be congruent. So if this side length is 5 inches, that means all 6 side lengths must be 5 inches, meaning the perimeter of this regular hexagon is 30 inches. So now all I have to do is just multiply this out, and I get that the area of this regular hexagon is 150 inches squared, or square inches. Okay, doing the same thing. We're finding the area of a regular polygon. This time it's a regular pentagon, meaning it has 5 sides. So in order to find the area of a regular polygon, we're going to use the area of a regular polygon formula, which is area is equal to 1/2 the apothem times the perimeter. In this figure over here, we are given the length of our apothem. It is the perpendicular distance from the center of our polygon to one of these sides. That's 4 feet. So that's going to go in for our lowercase a. But what about our perimeter? Well, we know that this little segment right here is 3/4 of a foot. We also know that our apothem bisects this given side over here, meaning that if this is 3/4 of a foot, this segment over here must also be 3/4 of a foot. So this whole side length then must be 3/4 plus 3/4, which is 3/2 feet. And because this is a regular pentagon, that means that each side length would be 3/2 feet long. So in order to get the perimeter, I would just take 3/2 feet, multiply that by 5, and I would get 15/2 feet. That is the perimeter of this given pentagon. Now all I have to do is just multiply this out, and I get that the area of this regular pentagon is 15 square feet, or feet squared. Now example 4 says find the area of the equilateral triangle below. Write your answer in simplest radical form. So in order to find the area of an equilateral triangle, which is a regular polygon, I need to use the area of a regular polygon formula. Area is equal to 1/2 the apothem times the perimeter. So I need to find both the apothem and the perimeter. So can I find either of those right now? Yeah, because I know this is an equilateral triangle, I know that all of these sides must be congruent. So if this side length is 2 rad 3 meters, that means both of these other 2 side lengths would be 2 rad 3 meters, meaning that the perimeter perimeter of this equilateral triangle would be 6 rad 3 meters. So I have found the perimeter. But now I need to find the apothem. So how do I do that? Well, in example 2, we already went through the steps in order to find the apothem of a regular polygon. The first step would be to find the measure of a central angle. So a central angle is an angle formed by the center of your polygon and the endpoints of one of the sides. So because they don't give you a center, you're going to have to draw one yourself, and then we're going to draw our central angle connecting that center with the endpoints of one of the sides. Now remember that the measure of a central angle is just 360 degrees divided by the number of sides in your polygon. Since this is a triangle, you just take 360 degrees, divide it by 3 sides, and you get that each central angle has to be 120 degrees. Then we're going to drop an apothem so that it's perpendicular to this side over here. Now, when we do that, there's 2 things to note. One would be that your apothem actually bisects this side over here, meaning that if the entire side length over here is 2 rad 3 meters, that means that each of these segments would then measure 1 rad 3 meters, or just rad 3 meters. The second thing to note would be that this apothem actually bisects our central angle. So in step 3, we're going to divide our central angle in half. So if the entire central angle is 120 degrees, we're going to divide that in 2 and say that each of these smaller angles in here are 60 degrees. Now you can see that we have created this small right triangle here where one of the acute angle measures is 60 degrees, meaning the measure of the other acute angle would be 30 degrees. So we have created a 30, 60, 90 degree triangle. Now with a 30, 60, 90 degree triangle, we can find the measure of our apothem. So how do we do that? Well, in a 30, 60, 90 degree triangle, everything is based on the short leg. So what is the short leg? That would be the side opposite our 30 degree angle. That's our apothem. The short leg times 2 gives you the hypotenuse. Well, we don't have that. But the short leg times rad 3 gives you the longer leg, the side opposite your 60 degree angle, which we do have. So in order to get our short leg, we just take that longer leg, rad 3 meters, and divide it by rad 3. So what's rad 3 divided by rad 3? That's just 1. So the measure of our apothem is going to be 1 meter. Now all we have to do to find the area of this equilateral triangle is plug our perimeter and our apothem into the area of a regular polygon formula. Area is equal to 1/2 the apothem times the perimeter. The apothem we said was 1 meter. That goes in for our lowercase a. The 6 rad 3 meters is our perimeter. That goes in for p over here. We then simplify, and because it wants our answer in simplest radical form, we don't just plug this in our calculator. We actually have to multiply this out. 1/2 times 1 is 1/2 times 6 rad 3. We just multiply the 1/2 times the 6. We get 3 rad 3 meters squared, or square meters. I say you try. You say you try. You try.
You try.
You try.
You try.
Okay, this time it wants us to find the area of a square. So typically when we find the area of a square, it's just base times height, or the length of a side squared. But we aren't given any side lengths. So what do? Well, we do know that a square is in fact a regular polygon because it has all sides congruent and all interior angles congruent. So we could use the area of a regular polygon formula, which is area is equal to 1/2 the apothem times the perimeter. Let's try to do that. So in order to use that formula, we need to figure out the apothem and the perimeter. So is there anything we can find first? Well, last time we found the perimeter first, but we aren't given any side lengths here. So we're going to try to find the apothem first. How do we do that? Well, in order to find the apothem, we know the steps now. The first is to find the measure of a central angle. So a central angle is an angle formed by the center of your polygon and the endpoints of one of the sides. So we're going to create a central angle by drawing a radius that connects the center of this polygon to this vertex over here. We have this central angle now. So how do I find the measure of this central angle? Well, it's 360 degrees divided by the number of sides. So in this case, it's a square. It has 4 sides. So 360 degrees divided by 4 gives you 90 degrees. That's the measure of this central angle. Next, what I'm going to do is drop an apothem from the center of my polygon so that it's perpendicular to this side over here. Now, there's 2 things to note about this apothem. One would be that it bisects this given side over here, but we're not given the side length, so that doesn't help us. The second thing is that it bisects our given central angle. So we're going to divide our central angle in half and make each of those smaller angles 45 degrees. Now you can see we've created this little right triangle over here where one of the acute angle measures is 45 degrees, meaning the other acute angle measure would also be 45 degrees. So we've created a 45, 45, 90 degree triangle. Now we can use our knowledge of a 45, 45, 90 degree triangle in order to find the length of our apothem and the length of half of one of our sides. So in a 45, 45, 90 degree triangle, the legs are going to be congruent to each other, and the hypotenuse, the side opposite our 90 degree angle, is going to be equal to rad 2 times the length of a leg. Well, if our hypotenuse is 5 rad 2 inches, then in order to get the length of a leg, I just divide that by rad 2, and I get that the lengths of both of our legs lengths here are 5 inches. Now what that tells us is that our apothem is 5 inches. So we got our apothem. Now we need to find the perimeter. So how do we do that? Well, we have the length of this segment right here is 5 inches. And we said that the apothem bisects this side over here, meaning that if the length of this segment is 5 inches, the length of this segment over here must also be 5 inches, meaning the whole side length would be 10 inches. And because it's a square, it's a regular polygon, meaning all of these sides must be congruent to each other. So all of these side lengths would be 10 inches, meaning that the perimeter would be 40 inches. So in order to find the area of this regular polygon, all we have to do is use the area of a regular polygon formula. Area is equal to 1/2 the apothem times the perimeter. We take our apothem, which is 5 inches, plug that in for A. We take our perimeter, which is 40 inches, plug that in for P. We multiply this out, and we get that the area of this square is 100 inches squared, or square inches. Now note, once we found this side length, technically we could have just found the area by using base times height, or the length of a side squared, and you still get 100 inches squared, or square inches. Now we get a challenge problem. So this says find the area of the regular pentagon below. Round your answer to the nearest hundredth. So this time we have a pentagon, but it works the same way. In order to find the area of a regular polygon, what you need to do is use the area of a regular polygon formula. Area is equal to 1/2 the apothem times the perimeter. So we need to find the apothem and the perimeter. Is there either one that we can just find right now? Well, since we know this is a regular pentagon, we know all sides and angles must be congruent. So if the measure of this side length is 4 centimeters, the measure of each side length here should be 4 centimeters, meaning we can find the perimeter of this regular pentagon right now. It's just 4 centimeters times 5, which would be 20 centimeters. Sweet. Now all we have to do is find the apothem in order to find the area here. So how do we find the apothem? Well, we got to go through our steps. So the first step in finding the apothem in a regular polygon is to find the measure of a central angle. Remember, a central angle is an angle formed by the center of the vertex and the endpoints of one of these sides. So here we have created a central angle in this regular pentagon. Now, in order to find the measure of a central angle, you just take 360 degrees, divide by the number of sides. Here, this is a 5-sided figure, so 360 divided by 5 is going to give you 72 degrees. That would be the measure of this central angle. Now we can move on to step 2, where we drop an apothem coming from the center of our polygon, so it's perpendicular to this side over here. Now there's 2 things to note about this apothem that we just dropped. The first is that it's going to bisect this side length over here. So if this entire side length is 4 centimeters, that means each of these segments in here would be 2 centimeters apiece. The second thing to note about this apothem is that it bisects the central angle as well, meaning each of these smaller angles in here would be congruent. So we can move on to step 3, which is where we cut this central angle in half. So if this entire central angle is 72 degrees, that means each of these smaller acute angles would be 36 degrees. Now this is where we would normally move on to the next step, which is where we use a special right triangle to find our apothem. However, this angle measure is 36 degrees. I don't know any special right triangles that have 36 degrees in it. So what are we going to do? How are we going to find the side length adjacent to this given angle if the only other given side length would be the side length opposite that given angle? Oh, well, maybe we could use a trig ratio because we do have a right triangle. We're given an angle. We're given the side opposite. We're trying to find the side adjacent. So what trig ratio could we use to find our apothem here? Well, what trig ratio involves opposite and adjacent? That would be tangent. So we could say tangent of our angle, 36 degrees, is equal to the side length opposite that given angle, which is 2 centimeters, over the side length adjacent to that given angle, which would be this apothem right here. We'll call that A. So now, how do I solve for this A? Well, I multiply both sides of the equation by A, divide both sides by tangent of 36, and now I have the value of my apothem. Now, I'm not going to plug this in my calculator yet and round it because you don't want to round till the very end. If you round too early, you'll get the answer incorrect. So we're going to leave it like this. So our apothem, we're going to write as 2 over tan of 36 centimeters. Now we can find the area of this regular pentagon by plugging in the perimeter and apothem in the area of a regular polygon formula. Area is equal to 1/2 the apothem times the perimeter. So our perimeter was 20 centimeters. That's going to go in here for P. Our apothem, we said, was 2 over tan 36 centimeters. That's going to go in for our A. Now we can plug all of this in our calculator. Make sure your calculator is in degree mode, not radian mode. Press enter, and you end up getting that the area of this regular pentagon is approximately equal to 27.53 centimeters squared, or square centimeters. So the only thing different in this question was we had to use trig in order to find our missing apothem. So if this is not a special right triangle, you need to use trig in order to find your missing side lengths of your right triangle.